All right, so it's time. Let us actually finally do it now. So we now describe you. Now we've said a lot. So again, I'm not going to write out every instruction one at a time, but I am going to write out a rigorous proof in terms of anything I say, anything I talk about. I will justify in terms of the things we've done already. So first of all, it's going to be a 3-ish string Turing machine, 3-tape Turing machine, I should say. I keep saying 3-string, but I really should say 3-tape. And when I say 3-ish, I mean it's really mainly a 2-tape machine, but you kind of need. I think you kind of need a third string to do some counting. You never really need a third string. It's just simpler. It doesn't really matter, right? Because even if it's a 50-string machine, it's still the same efficiency loss to collapse it down to a 1-string machine. A 3-string machine can be collapsed down to a 1-string machine that works in the quadratically more time, and a 50-string machine can also be collapsed down to a 1-string machine that works in the same time loss, which is kind of the result of the last proof. So it doesn't really matter how many strings I add. The point is that I'm going to use a multi-tape machine, and that will involve, that'll be a proof for a 1-tape machine, under the assumption that I can collapse it down, which I've proven that you can do. So, it doesn't really matter how many strings there are. The fact is that the important thing is that there's more than one. But as we know, that's fine. So as is typical, the first string will hold the input. And maybe I'll draw it out. So the first string, as is kind of typically the case with multi-tape machines, is going to be kind of it's going to be a read-only input tape. And then really the important second string is the work tape down here. Work tape. And then, if you want an output tape, you can have that too. Since this isn't going to have an exact string that the m of x might output, then if you want outputs, then you should probably put an output tape down here. But this is optional, so that's one of the reasons I say 3-ish. Because if you don't care about outputs, if you just care about having a machine that stops on all the same things, then or that halts in the same that accepts and rejects the same stuff, then you don't really need output tapes. So that's another reason I say 3-ish. There's a lot of reasons that you can say 3-ish. And then we might have one more string to act as a counter. But the main string is this guy here, the work tape. So the second string, so the first string holds input. That is the program code as well as the input that I want to use. Second string, what it's going to hold is the same at all times. The second string will always contain the second tape, I should say. I really need to start saying tape and not string. The second tape will contain a string representing the configuration, the current configuration of the machine being simulated. So that's what this is going to have. It's going to have the second string is always going to have the same thing. The second tape is going to have a string representing the current configuration, and configurations. We're going to code them a little different than usual. We're going to represent them a little differently than usual. Like I said, it doesn't really matter how you code configurations as long as you have the essential factors, which is kind of a description of where the cursor is, a description of what's on the tape, and the current state. So what we're going to do is we're going to have it parentheses, and remember that is part of the alphabet. The alphabet of our universal Turing machine is 0, 1, triangle, I guess, square bracket, square, blank, parenthesis, semicolon, parenthesis, comma. Oh my God. So I have commas and parentheses and the typical stuff pretty much. So configurations will be coded like this. They'll be coded like W, Q, U. And remember, these, every symbol is a number that's coded as a binary string, and all of them are the same length. So W and Q. So when I say W and Q are strings, what I really mean is that they're big strings of zeros and ones. But we don't really have to think too hard about that. W and U are strings, and Q is a state. And remember, it's all represented in binary, but that is kind of what it's going to have. The idea, so how does this code a configuration? The idea is that m of x, that if m of x currently looks like this, so if m of x looks like this, it's going to have like a string w, and then it's going to have like something here. Really, this is part of w, and then it's going to have another string u, and then the cursor is pointed right here, and it's in state q. Then cursor position is the final character of u. Or sorry, final character of w. And then u is the rest of the tape configuration. So basically, WU, this constitutes the tape configuration. If you concatenate the two together, this is the tape. This is the entire non-trivial contents of the tape. Everything to the left of W is just blanks. Everything to the right of U is just blank. So the entire tape configuration is given by the two of these together, and then you know where the cursor is implicitly, because the cursor is always going to be the last character of W. So that's the idea. So these three things, these two strings along with Q, do code the tape configuration, the state, and the cursor position, which is the entire configuration. So technically there's a step 0. I'm going to go ahead and address this now. So step 0 is evaluate if M is a valid Turing machine. If the string M codes a valid Turing machine. And again, this is, you can always kind of do this. I mean, there's a lot of ways to do this. I'm not going to go into too much detail on this, but like there's an essential syntax that needs to be there, and I'm sure it's believable that you can do this. I'm not going to get into the details of like context-free grammars or stuff to kind of justify why this is the case, but I mean, it's not hard to see that you can check if M codes a valid Turing machine, and if it doesn't, it doesn't really matter what we do if it doesn't. Just have cursor move right forever, let's say. It doesn't really matter what happens if the string doesn't code a valid Turing machine. We just need to check so that things don't, go wrong. So, it's going to be assumed that this does code a valid Turing machine, and if it doesn't, we'll just check that immediately and then have the machine never halt or something, or do something dumb if it doesn't. So that is technically step 0. So again, just to point this out, we have, this is going to have the input. It's going to have the machine, and it's also going to have, it's going to have, W, comma, Q, comma, U. It's going to have this, and the cursor will be somewhere. And so initially, we have to still do kind of an initial setup. So maybe I'll call this 0.5. Step 0.5. U will read its input and produce the configuration, the initial configuration, which is so it'll read all the way across and of its input tape, and it'll basically print this on its output tape. It'll print a single triangle. This is where the cursor is going to be, obviously. This is where the cursor would be for M, and then it'll print and then QI, and then X. So, I mean, given our input, given our coding of configurations, this is what the initial configuration should look like. So, just to kind of make sure everybody's on the same. Oh my God. Yeah. So, I mean, if the machine looks like if our machine M that we're simulating is supposed to look like this. Remember, the initial setup is always assumed to look like this. We're pointed here at state Q. Then this should correspond with, on our work tape, a configuration that consists, remember, WQU. The cursor is pointed here, so it'll look like this guy. It'll look like it'll have a parentheses in one slot, and then I'll have a triangle. And then this triangle, just this one triangle. And of course, this is not just one cell. This is, several cells coding a triangle in binary. So it's not an actual binary. It's not an actual triangle on our universal Turing machine. But it does represent a triangle, and then there'll be a comma, and then there'll be QI, and then there'll be, and again, this is also not just a single cell. This is multiple cells. It's the same number of cells as this guy. It's coded in binary, and then it'll be X, and then it'll be a parentheses, and then that'll be it. And so this is also, not one single cell. It's a multiple of the number of cells that's used for these two. It's several symbols that are kind of coding X. ... Actual blanks coded like that. So this is kind of what the configuration is going to look like at first. So this is use work tape. So that's the convention. So the work tape will always have a complete description of M. It'll have the configuration. And yeah, so now that we read the input, we produce this. I'm sure it's easy to believe that you can do that. And now we actually have to describe a single step. And so, one last thing. Of course, if well, I'm not going to say that yet. So now, much like the previous things, much like the previous proofs we've done, I'm at a point where if I can just describe how to simulate a single step of the machine M, then I'm done. Right? We've talked about this many times already. So now we describe how to simulate a single step of M of X in general. If I can do that, then I'm done. That's why I said this was step 0 and 0.5. Everything I've set up until now is sort of just preliminary housekeeping. So what are we going to do? Well, okay. So what we're going to do is maybe I should also say this before I start to describe the simulation. One more tiny piece of housekeeping is before starting. So after printing this guy here, the initial configuration, move cursor, to the beginning, to the first parentheses. So move this cursor to the first parentheses, and this one to the left. Maybe I'll just draw it. It's kind of hard to say. So if we look up here, the initial setup is going to end up looking like this, where basically what I'm going to have is M is equal to So cursor will be at the left of this. So I mean, remember it's going to be parentheses, parentheses, stuff in here, dot, 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 parentheses. And so I want my cursor to be right here. So that's where the cursor will be on the first work tape. That's where the cursor will be in the beginning on the input, and then where it'll be on the work tape will be, let's just say right here. Let's just say we start there too. So move cursors to the correct positions. To the appropriate positions. Okay, now we can describe a step. So now we describe a single step. So here's the stuff. So step 1. You will scan right across the second tape, I'm going to call it the configuration tape. Until finding the binary description of a state. So the cursor here is going to move right until it encounters this guy right here, until it encounters the first state. Encounters a description of a state. I want to return to this step a little later, but that's what I'm going to do. That's all I'm going to say for now. Step 2. So once it finds a state, it then doubles back to cells. Remember, a cell is going to be a string of zeros and ones that represents, in length one symbol. So it's going to move over here, and then it's going to double back twice to get to the previous symbol to detect the cursor symbol. So if we'll move to this, and then we'll move back here, and then at that point I'll have my symbol state pair. So once it has that information, what it's going to do then is it's going to, with symbol and state detected, machine U will move input tape cursor of input tape right in search of a matching, let's say, symbol. Let's say state, actually, I guess. In search of a matching state. So we're going to begin to move through our instructions looking for a matching instructions. We'll start by looking for a state. If it finds one, if it finds a matching state, it doubles back to check if the symbol matches. So basically, remember, the instructions are coded like this, where we have parentheses, parentheses, symbol, state, and then instruction. So we're going to kind of move our cursor this way until we find a state, and then we're going to double back, and then we're going to check it. We're going to check if the state matches, and then if the state matches, we're going to double back and check if the symbol matches. Doesn't really matter the order, but I guess we'll do it that way. If it doesn't, it goes back to step 3. If it does, go back to step 5. So now if we get to the big one. Now we need to edit. So now we know what state and symbol we were looking at. We found the matching instruction. Step 5 is edit the configuration. And so that's the big part of what we need to talk about. How do we edit the configuration? Okay, so I've drawn a picture here of kind of what the setup is, because we need to think about this very closely to make sure we get it right and can analyze the complexity kind of effectively. So, I've drawn, this is my input strings, and we're looking at the specific instruction here. So we've got a matching symbol. So we've got a matching symbol and a matching state. You can see that those match here. And basically what's here, this is just stuff. So this stuff, and then finally this last symbol, this stuff here constitutes W. So this is the last symbol of W, and this is Q, and then this is just what all of U, whatever U is, and then blanks going forward, blanks going backward over, and then blanks going forward, blanks going backward over here. So we've got W with the last symbol is sigma, Q here, U here, and then likewise up here we're looking at an instruction. And so what do I need to do? Well, obviously I need to replace sigma. At the minimum I need to replace sigma with lambda, because that's what it's telling me to do, and I need to replace Q with Q prime. So obviously always need to replace sigma sigma with sigma prime, Q with Q prime. That's the obvious thing to do, but there's not much to that. Obviously those steps are simple. Then need to rearrange based on the direction. And that's kind of the part that requires a bit of thought. First of all, if d equals 0, done. Right? I don't need to rearrange at all. But the other ones we're going to have to address in cases because it gets kind of confusing. So case d equals 1. Let's start by the d equals 1. So if d equals 1, then the cursor will be on the first character. Then what's that mean exactly? Well, if d equals 1, then that means that our cursor for m is supposed to move right. Let me go ahead and kind of show it. So here's m. This is the actual machine that we're simulating. It's going to have W-ish. So it's going to have stuff followed by sigma, which we've replaced with lambda. And the cursor is here. It's in state Q prime. Well, maybe I should put 2. Let's say. So I got sigma here. I'm in state Q prime. I'm in state Q. And then I've got U here. Well, let's just say U1 and then rest of U. So I've got that. So that's kind of what it looks like. And then after doing the instruction, what it ends up having is it's got the stuff, and then it's got sigma, and then it's got U1. That's where the cursor is now, and then rest of U. So the division between W and U has to change. I have to bring the first character of U over to this side. So that's going to require some rearranging, but that's the rearranging we have to do. So what do we need to do? So let's draw it out. So I have, I'm going to assume that I've already replaced sigma with sigma prime, or I guess sigma with lambda, really. Sorry, I shouldn't have said sigma prime. There we go. Well, let me go ahead and just kind of say what I want. So I've already replaced this guy and this guy with what I need. So I've replaced this with a lambda and this with a Q prime. And what I need to do is I should probably edit this. I have really a U1 over here. And then rest of U. And then blanks. And then, sorry, in the parentheses and then blanks. And so what I need to do is I need to rearrange these 3 symbols specifically. There's no other things I need to rearrange. So what should I do first? So let's go ahead and, as a first step, swap this with this. So we'll switch these symbols out, and then we'll switch these 2 symbols out. We'll change Q for Q prime. We'll change sigma for lambda. And then what we're going to do after that is we're going to swap U, the first character of U, with this first comma. And those are going to be set things. Those don't, there's no searching I need to go. I need to go exactly 1, 2, 3, 4 characters over, and then swap that with what's exactly 1 character over. So once I've done that, what I have is stuff. Lambda is still here. but now I have a U1, and then I have a Q prime, and then I have a comma, and then I have another comma, and then I have the rest of U. And so what do I need to do now? Well, now I need to swap these two guys. So if I swap, well, maybe I'll put it up here. So if I swap this, and then I swap this and this, then what I get is exactly what I need. I get a comma here, and then I get a Q prime, and then I get another comma, and then I get the rest of U, and that's exactly what I need. That's exactly what the new configuration should look like. So 2 character replacements, 2 swaps, and I'm done. Now, there is an assumption there, unfortunately. So steps, so I'll just type it out. Whoops, no. So replace sigma with lambda, Q with Q prime, swap first comma with last character of U, and then finally swap Q with second comma. Now, that'll do, assuming that there's something over here. That'll do, assuming that U1 exists. So, this assumes that there is something to swap. This assumes there is an available character to swap. What do I mean by that? Well, if U is the empty string, well, what would that mean? That would mean we have basically I have let's just say W equals W1, W2, ... Wn, or maybe I, let's say. W1, W2, ... Wi. This is where the cursor is. Well, and then let's just say that this is the edge of the tape. Everything to the right is just blanks that I've never explored before. So, i.e., so what it would mean for U to be the empty string would be this would occur if everything to the right of the cursor is uncharted territory. And what that would correspond to as our configuration is it would correspond to ... blank, parentheses, stuff. Maybe I should say W1, W2, ... Wi, comma, Q, or lambda, Q, and then comma, and then it would just close off with the parentheses there. And so in that case, this kind of algorithm that I wrote out for doing the swaps, that doesn't work. I can still do this first step where I replace sigma with lambda and replace Q with Q prime. Let's go ahead and do that. So I replace Wi, that would be sigma in this case, with lambda and Q prime. I can do that step, but there's nothing to swap over here. I have to do something. So in this case, what should it be? Well, if my cursor is over here, then technically what I have is a coded blank that is now on the side of W. So W, what I need W to be replaced with, oh my god, W1, w2, what the heck, w2 dot 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 wi should end up being this string that represents the left side of the tape will end up being replaced with w1 w2 dot 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 lambda instead of wi, and then a blank. That's what it's going to be. So I need a coded blank. Remember, the blank is, even every symbol of the machine is, every symbol of the machine M is coded as an integer, including blanks. So what I need to add is a coded blank. And so what I need to do is I need to add room for it. So what I'm going to do is I'm going to move my cursor here. And then run space creating subroutine. An appropriate number of times. I'm going to have to use it more than once to make room to record my coded blank. Then record the coded blank. So basically what that'll end up with, what that'll leave me with is, maybe I'll just record it here. What that'll leave me with is a blank, but it's coded blank. This is not a blank. This is several things. This is a binary representation of M's blank. But then I have a comma, and then I have Q prime, and then I have another comma, and then I have close parentheses. Yeah, the stuff to the right is still nothing. I just need to make a coded blank on the left side here, and that's what I need to do. So if there is something to pull over, then I just have to do swaps. If I don't have anything to pull over, if I'm in uncharted territory and I'm moving right, then I need to create some space that moves the whole string to the right over. But note that the whole string is just exact. It's always, in this case, 1, 2, 3, 4 symbols. So the subroutines, the subroutine doesn't depend on the length of the input string at all. In fact, nothing I've described here relies on the length of the input string. I'm just swapping around characters of fixed length. So all of the computational complexity of doing any of this, it has nothing to do with the actual input length. It's just overhead based on the complexity of the machine itself, M. But it has nothing to do with X, and that's going to be an important thing to note. Even this moving everything to the right, it's just fixed to be 4 things no matter what. So that's the case d equals 1. And then if d equals -1, do I want to go over this? Yeah, I'll go over this. If d equals -1, it's going to be similar, but it actually ends up being simpler. I'll go ahead and skip ahead to when I've finished drawing this. So this is what the tape looks like that I'm simulating. I've got the string W on the left side, which is, the last of which is what's pointed at. That's in state Q, and then I'll skip ahead again to what I want it to look like. Okay, so this is what it's going to look like afterwards. So this is the step. If d equals -1, I'm going to replace the sigma with a lambda, but then I'm going to move my cursor to the left. And so what does this correspond to? What should this correspond to for our configuration? Well, the new W, the new string on the left, is going to need to be W1, W2, dot, 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 up to Wi minus 1. So it doesn't include the symbol I replaced. New U is lambda U1, U2, dot, 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 Uj, where Uj is equal to U. Or U1 through Uj, this string of characters is equal to U. So that's what I need. So let's go ahead, and I'm going to skip ahead once more to draw out this line, draw out what it looks like on our configuration tape. Okay, so obviously the first step here is going to be to replace lambda here with Q prime. So right here, this is what's actually going on for M. If I was just running the machine M on its own, this is what it would look like. I would replace this with this and move to the left. I'm trying to simulate that and figuring out what it would do to my configuration. And so this is what my configuration looks like. This is what the configuration tape looks like, and I'm trying to figure out what to do. So what do I want? I've got W1 through Wi minus 1 and lambda. That's what W looks like right now. That's what the left side of the tape configuration looks like. And I've got U1 through Uj here. And what I want is I want the new U, the new thing on the right, to be lambda followed by all that. So I need this lambda to be over here, and I need to have space for that, technically. And then I need to have all this moved over. So how can I do that? Well, I don't think anything's going to change to the left. Obviously, this is going to be the same. But what I want is W1 I want Wi minus 1, and then I want a comma, and then I want Q prime, and then I want another comma, and then I want lambda, and then I want U1, U2, Uj, and then blanks. So this is what I want. And so how do I get there? Well, I can get there by first swapping the lambda with the second comma. If I swap the lambda with the second comma, what's that get me? It gets me a second comma here and a lambda here. So now U looks almost right. And then I just need to swap these two. And that's it. And the thing to note is that always works, because there's always something over here. So since W is never empty, don't need to worry about running space creating subroutine. Don't need to ever worry about making space. You can always do this step. You can always do the case where D equals -1 with just swaps. So you can always handle this case with swaps, and that's it. All we have to do now is kind of reset things. So let's write out step 6. Once done editing, move cursor to the right to move cursor of input tape back to the beginning of the transition function. Beginning of the transition function. And you can do that by detecting 2 parentheses in a row. 2 left parentheses in a row. Or 3, actually, I think. 3? Yeah, 3. And then where am I going to be left here? Well, I'm always going to be left, if I swap this with this, and then this with this, I'm not going to think too hard about it. The bottom line is that I need to be here in both cases. So I'm going to need to double back. It's always going to, the important thing is that it's always doubling back in both cases. So then, move, we're going to move both cursors to the left. So this is going to be moving left. And then also, move configuration tape cursor left to cursor symbol. So basically, where this is going to end is it's going to be either here, like at the end of W, for the cursor tape. It's going to be that in both cases. So I think that only involves like one jump back. It's a fixed amount of space that you need to jump back. It doesn't depend on the input. And that's in both cases. We basically want to end every step with our cursors kind of in a standardized location, where yeah, we're basically, I don't really see a good place to kind of illustrate it, but I think you know where you want to end both cursors. But we need to move both cursors left to reset things, and then we just start the process over, and we've described a full step. We've described the loop at that point. That describes an entire step. Now, okay, so I just wanted to interject. There's a couple things I forgot to say. I said this describes the universal Turing machine, and then ended the video, and then realized I didn't really talk about what it means to halt, what it means to do an output. So let me just say that real fast. If in step, let's see, which step is it? There's a lot of stuff. At this point right here, when we find a state in step 1, so if at any point when in step 1 detects a halting state. So if in step 1, when you're detecting the state of the configuration and you detect a halting state, you should also halt. In the same manner. So if the machine M is halting in an acceptance state, then you should also halt in an acceptance state. If the machine if the machine M halts in rejection, then you should also halt in rejection. And if it's supposed to give an output, if M is supposed to give an output, we can always add a final phase. In which U transfers the tape configuration onto an extra Turing machine, an extra tape. And halts. So if you're supposed to halt, the thing is, we have configurations written in the tape, right? We don't have the actual output. We don't have the actual tape configuration. Remember, M of X. The interpretation is that the tape configuration of M of X is the output if M halts. And so if we want to have the actual outputs be the same, then what we really have is we have parentheses W Q U parentheses, and so what we would need to do is go into some extra phase in which we print on an output tape before halting W and then U without any extra commas or parentheses, and then halt. So we would need to do that too, but that's fine. But that's how you halt. That totally fully describes the Turing machine. So just wanted to add that in. So that more or less describes the entire universal Turing machine. This describes the universal Turing machine. So, now that I've finished describing it, I want to, I think I'll stop the video here and start up a third one where we talk about what we did, kind of justify, what I didn't explain in terms of how much I need to say to make this rigorous, and also analyze the complexity. But I think I'll pause the video here and continue that in the next video so the links don't get too long.